Let us take a simple example first to apply this formula. The example is this gun or cannon which is free to move on the horizontal surface, and the horizontal surface is smooth, fires n number of bullets or n number of shells per second. In each second, in 1 second, it can fire n number of shells or bullets with the muzzle velocity v. What is muzzle velocity? Muzzle velocity is the velocity of the bullet with respect to the gun. Velocity of the bullet with respect to the gun. That is muzzle velocity. We have to calculate the impact force acting on the gun by the outgoing bullet. When the bullet will be triggered, when the gun fires the bullet will get out of the gun and give a backward kick. That kick is the impulsive force or impact force. Using this formula, we can calculate it. The impact force is equal to relative velocity between the bullet and gun into the rate at which the variable mass system is changing its mass. The relative velocity is nothing but the muzzle velocity. With respect to the gun, the bullets are moving with a velocity, that's the muzzle velocity, that's given, that's V. dm by dt means per second the rate of change of mass, per second how much mass is changing. You can just write rate of change of mass of this variable mass system, gun plus cannon system, is equal to number of shells fired per second into mass of each shell. It's very easy to understand. So that is V in number of cells per second, N, and mass of each cell, let it be M. Mass of each cell. This is given, this is given, this is given. So the impulsive force or the impact force acting on the gun depends upon the muzzle velocity, it depends upon the number of shells fired per second, it depends upon the mass of the cell. Let us take another example. This is a water jet coming out of a tube, fixed tube. The tube does not move. The cross-sectional area of the tube, let it be A, and the velocity of the outgoing water, let it be V. Find the reaction or impact or impulsive. Reaction force can be called impact force, can be called impulsive force. All these terms bear same meaning. First of all, write the formula. The impulsive or impact force is equal to relative velocity times the rate at which the mass of the variable mass system is changing. You can write it capital M or small m, doesn't matter. Let us first consider the scalar aspect of this formula. dm by dt is the amount of liquid going out per second, and relative velocity between the liquid and the variable mass system, that is the tube, we can call is V, because V is the velocity of the liquid with respect to the tube or relative to the tube. Amount of liquid going out of the tube in 1 second can be given by equation of continuity, that's equal to A into rho into V. So we are getting the impulsive force A rho V square. In which direction? The tube will be kicked by the outgoing liquid in backward direction. To understand this point, why should the direction of the impact force acting on the tube is backward? Let us analyze this formula. For this purpose, we have to write the formula in vector form. If you look at this term, U relative or V relative, velocity of the outgoing liquid with respect to the tube is in positive direction. Whereas this factor, this is the vector quantity, this factor is a scalar. It can be positive when the mass of the system increases. It can be negative when the mass of the system decreases. It can be zero when the mass of the system does not change at all. Since we consider this part as a variable mass system, while the tube loses the liquid, its mass decreases. Therefore, dm by dt is negative. When this is negative and this is positive, you will get the force in negative direction, negative x direction. This is some sort of vector understanding. Mathematically or vectorially, if you understand this, minus I cap signifies that the force acting on the tube is directed in negative x direction. In other words, we can say that the tube is kicked behind or kicked back by the outgoing or emerging liquid. Let us take another example. of equilibrium of a ping pong ball when you keep it on a water jet coming out of a vertical tube. The water jet comes out vertically, and when it moves up, its speed decreases, not increases, its speed decreases, because it has to obey the conservation of energy. Here more speed, this is the tube, it gets out of the tube with certain velocity. Since it goes up, its velocity decreases. At a particular height, when you place a ping pong ball, this ping pong ball will experience an upward impact force which can nullify the effect of its gravitational force. So called the weight of the ping pong ball will be counteracted or balanced by the impact force. In that case, the ping pong ball will remain in equilibrium. We have to calculate that particular height at which the ping pong ball will remain in equilibrium. At this height, let the ping pong ball stay at rest. For this, let us assume that water falls dead just after colliding the ball. The ball will experience an upward impact force which will nullify the downward gravitational force. These two forces will be equal and opposite. For equilibrium of the ball, the acceleration will be equal to 0. Therefore, the net force will be equal to 0. The net force will be equal to impact force upward and gravitational force downward will be equal to 0 when you add them vectorially. Impact force is equal to V relative dm by dt minus mg will be equal to 0. Mass of the ping pong ball, let it be m naught. Dm by dt is the rate at which water is striking the ping pong ball, and that is equal to rate at which the water is coming out of the tube. Here dm by dt, here dm by dt are equal because we have to apply the concept of equation of continuity for this streamline, and that is equal to a rho into v. Base the velocity, here area into here velocity, or here area into here velocity. Here area we cannot calculate. What is the effective area at which the water is striking, even though you can calculate the velocity here. Therefore, we can use area of the tube and the velocity of the liquid at this point into the density of the liquid. Let the velocity here be v naught. Here the velocity let be V. Velocity of the liquid with respect to this system minus or is equal to m naught into g. So V equal to m naught into g by area of the tube by the density of liquid by the velocity of liquid at the time of getting out of the tube. Applying Bernoulli's equation at these 2 points, here pressure is atmospheric pressure, here pressure is atmospheric pressure, here kinetic energy per unit volume is half rho v square. With respect to this point, the gravitational potential energy per unit volume is rho gh. Here the pressure energy per unit volume is P naught, that is atmospheric pressure, because already we have taken the point which is exposed to atmosphere. This point also is exposed to atmosphere. Here the kinetic energy is half rho into v naught square, not v square, because here the velocity is v naught, plus with respect to this reference level, here the height is 0. So you have to equate these two. That is what we call Bernoulli's equation. While doing so, we can get this factor cancelled from both the sides. P naught and P naught will get cancelled. Therefore, V can be written as v naught square minus 2gh square root of this. This is equation number 2. Substituting V from equation 2 in equation 1, we can calculate the value of H. Putting V from equation 2 in equation 1, we get v naught square minus 2g square root is equal to m naught j by a rho v naught. So we can write H equal to v naught square minus m naught square j square by a square rho square v naught square upon 1 by 2g. So assuming that the water falls dead just after the colliding the ball, find the value of the height at which the ball will be in equilibrium. That is the question, and this is the solution, and we are getting this answer. This is based upon the reaction force formula, V relative dm by dt.